Okay, hi guys. So we'll be continuing on seeing the derivation. So suppose z can be written as a function of x comma y, and suppose we have to calculate the delta z. So delta z can be written as z of x plus delta x, comma y plus delta y minus z of x comma y. So in other words, I can also write that delta z would be equal to z of x plus delta x, comma y plus delta y minus z of x comma y plus delta y plus z of x comma y plus delta y minus z of x comma y. How are we arriving at this conclusion? Okay, so for the same I can write that write that let's suppose pictorially we have point A and point B. Point A is x comma y and point B is x comma delta x and y comma delta y. Okay, and on the top of it we are having these 2 points as functions of z. Okay, so we are considering that z is a state function, so we can write that z of a to b can be written as z from a to c and from c to b. Okay, this is not b to c, this is c to b. Okay, so z of a to b, as z is a state function, can be written as z of a to c plus z of c to b. Okay, so we can write that a to c can be written as z of x plus y, x comma y plus delta y minus z of x comma y. So this is a to c, and from c to b we can write that z of x plus delta y minus comma y plus delta y minus z of x comma y plus delta y. So we can write all these things in terms of we can write z of ac and z of cb, and from the same we can write or derive z of ab. So this term is nothing but, I am first writing, so this is the addition of these two terms, so I am just adding these two terms. So this is cb, so this is c of cb, z of cb, which can be written as z x plus delta x comma y plus delta y minus z of x comma y plus delta y plus this is z of ac, which is z of x plus delta y minus z of x comma y. So I hope you are following this. So I can write delta z in this form. So this question is clear now. Okay, so now what I can write is, so when we apply limits, which is delta x tending to 0 and delta y tending to 0 in the two terms which we have just seen above, so I'm just writing it again, that delta z would be equals to z of x plus delta x comma y plus delta y minus z of x comma y plus delta y. So this was the first term. I am multiplying and dividing it with delta x. Okay, and applying the limit x delta x tending to 0 on this term, and adding the another term which was z of x comma y plus delta y minus z of x comma y divided by, and multiplying it with y. So and applying limit delta y tending to 0 here, so this term can be written as del z upon del x times dx, del z upon del x at constant y times dx, plus this can be written as del z upon del y at constant x times dy. So finally we arrive at this equation in which z, which is function of x and y, can be written as this differential form. This is as we are applying limit here, so this is limit delta x tending to 0 and delta y tending to 0, so here it would be dz, not del z, not delta z, it would be dz. Okay, now using the same, consider that another state function which is u can be written as function of temperature and volume. So similarly, du can be written as del v upon del t at constant, this is del u rather, as z is compared to u, so this is dz, so this would be del u divided by del t at constant volume times change in del t, or change in temperature, or slight change in temperature to be particular. So it would be the second term would be del, it would be del u upon del v at constant temperature times dv. Okay, so this is the equation which we get when used at function of temperature and volume. Okay, so for an ideal gas, what we can write, we can say that u is a function of temperature only. Okay, it is independent of volume, so internal energy of ideal gas depends on temperature only, depends on temperature only. So we can write that u is equals to kinetic energy plus potential energy. Okay, so as it is only dependent on temperature, so we can write it won't have any effect with change in volume, so we can write that dv would be equals to, or rather change in temperature is not having any effect on change in volume, is not having any effect on du, so we can write that du so we can write that du upon, or rather del u upon del v at constant temperature would be equals to 0. So therefore we can write that du would be equals to, this term won't be there, so this term would be 0, so we can directly write this term only, so it would be del u upon del t at constant volume times dt. Okay, so we know that del u upon del t at constant volume can be written as Cv, because we already know that at constant volume du dw is 0, so du can be written as dq. Okay, and du can then be written as Cv dt. So we can write that du upon dt at constant volume would be equals to Cv, or we can write del u upon del t at constant volume equals to Cv. Okay, so with the same understanding, I can write del u upon del t at constant volume as Cv, so du would be equal to Cv dt. And similarly, we can write that molar internal energy change, which is dum, can be written as Cvm dt. So these two are important formula which we have just derived. So with this, we'll end this lecture. So we'll meet in the next lecture. So till then, good luck and goodbye.